All right, welcome everybody. Just going to give another minute or so to give people a chance to join, and we'll get started shortly. All right. Hello, everyone. Welcome to the Mid-Atlantic Biosolids Association webinar series. We're pleased to have everybody join us today. My name is Lauren Miller, and I'll be your moderator. We have two great speakers today. The first speaker is Dr. Scott Grieco, who will be presenting on PFAS and wastewater and biosolids. Our second speaker is Sudhakar Viswanathan, who will be presenting on Is Complete Destruction of PFAS and Sludge Possible? Experimentation and Challenges of Combining Thermal Dryer and Thermal Oxidation to Treat PFAS-Laden Sludge. These two presentations will be capped off by a 15-minute technology overview on methods for assessing health and environmental risk of organic micropollutants in biosolids by Dr. Stephen Zemba. Before I hand the mic over to our speakers, I have a few housekeeping items to cover. First, be aware that your microphones are muted and your video has been disabled. If you can hear me, you've done it right. Next, each presentation will be about 25 minutes with 5 minutes for questions at the end of each talk. Finally, we'd love to hear from you during today's presentation. If you have questions for any of our speakers, please use the Q&A feature, which is on the bottom of your screen. You just move your mouse around, it'll pop up. You can ask these questions at any time during the presentations, and I will go ahead and ask them during the Q&A portion after each presentation. Today's webinar will be available as a recording after the live session. An email with the link to the recording will be sent out after the webinar series is over in mid-August. Without any further ado, I'd like to kick things off by welcoming our first speaker, Dr. Scott Grieco. Dr. Grieco has over 27 years of experience in the evaluation, design, and optimization of industrial wastewater treatment systems and is recognized nationally as a PFAS subject matter expert. He's currently serving as the technical director on several studies to evaluate treatment approaches to PFAS in leachate, biosolids, water, and wastewater. Dr. Grieco leads multidisciplinary teams of engineers and scientists, interacts with senior technologists and management, and works directly with client senior leadership in assessing technical solutions, minimizing projected life cycle costs, and reducing environmental liabilities at industrial facilities. Prior to joining Jacobs, he directed activities for a private technology development and treatability testing laboratory. Under his direction, bench and pilot scale technology development programs were completed for precipitation, adsorption, biological treatment, advanced oxidation, and electrocoagulation. Dr. Grieco, over to you.
Thanks, Lauren. Let me just share my slides here. All right, I assume everyone can see that. So today I'll be talking a bit about PFAS and wastewater and biosolids. Just by way of background, I think a lot of people have been inundated with PFAS 101, but just some highlights, related to what we're going to be talking about from a wastewater and biosolids perspective. Per and polyfluoroalkyl substances, or PFAS. They're a large family of compounds, which are more than 4,000 that have been currently identified academically, but we only commercially analyze for less than 30. So in and of itself, that shows a bit of a data gap in terms of what we know and what we're focused on from the PFAS family. It's certainly a very nice, neat acronym, but certainly a lot of compounds with varying different types of chemical properties and physical chemical characteristics. The per and polyfluorinated nomenclature means that they have organic chains of carbon and fluorine, which are bonds are very strong, one of the strongest known in nature. So these compounds don't degrade naturally, and they're also very difficult to destroy through engineered treatment. Oops, I forgot to click the slide. I apologize. So there are many industrial, commercial, and consumer uses of these materials. Although the concern with PFAS was initiated about a decade ago with military use of what's considered aqueous film forming foam, or AFFF, we've come to realize that the prevalence of these compounds are more than just that, and they go completely across our modern society. As we've understood more of where PFAS are used, we're understanding the impacts of PFAS on our waste management processes, including wastewater and biosolids. Let's see. There we go. Okay, I got it moving now. We can find point source contributions to wastewater treatment plants related to various industries and landfills, and non-point source contributions may be considered things like drinking water that passes through households and back into the wastewater sewer. But it's important to point out that even if a community doesn't have PFAS in its potable water, we do see PFAS in household discharges. Why? Because there's a consumer use of various products within households, which may be sources within themselves. Common products that we use, such as stain-free clothing, cosmetics, skin lotions and treatments, food wrappers, and packaging that may end up getting washed down through the drain if you have a disposal. Those all contain various levels of different types of PFAS. And of course, we're contributing some fraction through human bodily excretion, as if you've seen data in terms of blood serum levels, all of the developed worlds, they have populations, we all have some level of PFAS in our bodies. So as the half-life of that is long, and it takes a long time to release, there is contributions from us as individuals as well. So let's take a look at a typical wastewater treatment unit operation. Of these, chemical coagulation, precipitation, membrane separation, and adsorption are really the only unit operations that can reduce or eliminate PFAS. It may be a surprise to some people listing coagulation, but it does remove some PFAS. It's often more effective on longer chain and sulfonic acid PFAS. Even with standard commodity coagulants, 30 to 60% removal can be achieved. And we observe that the level of effectiveness is dependent on concentrations, compounds, and certainly background water chemistry. RO, although effective for PFAS removal, is most applicable for water reuse or groundwater recharge applications, and obviously is not a common for wastewater treatment plant when it's being discharged to surface water. But when applied, the PFAS in the RO reject still does require to be managed. So we're basically transferring it from one liquid stream to another liquid stream. So we're really just passing it from one place to another, and it's really not being treated. So that requires additional consideration if you're considering RO at the back end of a wastewater treatment plant. Adsorption via GAC and ion exchange are the go-to approaches for drinking water treatment. And these technologies have limitations, certainly when applying them to wastewater effluent. They will require significant pretreatment for solids, background organic carbon, and inorganic interference. I'd also like to point out that although not widely commercially applied yet, there are a new set of novel adsorbents being piloted, either manufactured or modified natural adsorbents that have much more selectivity for PFAS, and they're not as negatively impacted by background compounds, which these adsorbents in and of themselves may be more applicable for adsorption if we're looking for treatment of PFAS in the wastewater stream. So what's the disposition of PFAS within a wastewater treatment plant? Well, this table shows influent for an effluent for two common, two example wastewater treatment plants, I should say, Plant A and Plant B, and 5 common PFAS were measured as part of this study. The first thing you can see when looking at the individual PFAS is that there's no reduction across the wastewater treatment plants. But moreover, you can see that the PFAS concentrations, if you look at the total column at the end, these actually increase between the influent and the effluent. And this is really apparent when you look at Plant A versus Plant B. Plant A increases by 25%, where Plant B increases by a factor of 3.4. This is what we typically observe across wastewater treatment plants due to what's considered precursor conversion to measurable terminal PFAS. So precursors are considered any of those 4,000 compounds that we don't actually analytically measure for. And many of the precursors are actually, they're not stable compounds, they can be converted. And when they're converted, they're not destroyed, but yet they're converted to actually the what we consider terminal PFAS that we actually measure, the 24 or 30 compounds that we actually measure. And this conversion is caused by both physical chemical processes such as aeration, which will oxidize those compounds and convert them to terminal products, as well as the biological aeration, biological oxidation in and of itself, aerobic biological oxidation. You can see that the magnitude of change is not the same, and it's certainly a function of the type of PFAS sources that are being received at the plant. And of course, the other aspect is not only the PFAS exiting the plant through the liquid effluent, but these PFAS are also retained in the biosolids. In the US and Canada, a substantial portion of the biosolids are land applied. And this is a cost-effective disposal method that benefits both the utility and the agricultural land. Landfills don't desire these materials as they take up usable landfill volume, and they like to reserve these for what they would consider higher value products, such as municipal refuse. So although the current understanding in the science around PFAS fate and transport in the environment is developing, there is increasing concern with surface runoff, groundwater infiltration, and possibly even plant uptake when it comes to PFAS in land-applied biosolids. In fact, even without specific regulations, there's examples in parts of the US where farmers are refusing biosolids because of their concerns. So are there regulations related to PFAS and biosolids? Well, not necessarily specifically, but what I would say is 2 things. At the federal level, the EPA is in investigation and development mode. The PFAS Innovative Technology Team, known as PIT, is actually finalizing analytical methods for biosolids and evaluating thermal treatment technologies around biosolids and in other thermal approaches not having to do with biosolids, but biosolids is definitely one of their focus. And the EPA overall is targeting to have biosolid action plan this year and targeting screening values and possible regulations in 2021 and beyond. As with drinking water, several states are on what I consider a parallel or maybe even a faster trajectory than the US EPA. To date, Michigan has completed probably the most comprehensive study of wastewater utilities and biosolids, and I'll be reviewing some of that data in the next few slides. Michigan is leveraging the industrial pretreatment program within that state to reduce PFAS from industrial sources and have drinking water and ambient water quality standards in place. But they do not have any specific guidance values or regulations for biosolids. I think many people are aware that Maine has biosolids specific screening values, and I believe Steve Zemba, who will be talking at the end, will talk about this in a little bit more detail. In other states like California and Wisconsin are in the investigation and data collection mode, and more states are being added to that list. So what's the numerical guidance values or regulations that exist? There are values that are established to be protective of groundwater. The concern is that soils containing PFAS, which are located over shallow groundwater aquifers, the precipitation will solubilize the PFAS in the soil and transport the PFAS into the potable aquifer through percolation. As I mentioned, Maine has established biosolid screening values based on this pathway. And in addition, 6 other states have soil values, not biosolids values, but soil values in general that they've established to be protective of groundwater. And you can see those values there. Of note, there's also a concern of the uptake pathway from crops, from soils to crops and livestock. The science on these pathways is still developing, and so there's no current screening values exist for this exposure route. So these values are all to be protective of groundwater and don't reflect any other pathways such as uptake pathways. So what do we see in terms of PFAS and biosolids? Well, the first thing to point out is that PFOA and PFOS, the 2,8-carbon PFAS compounds, they've been the primary focus of concern and study, and certainly have the most data around them, both from a field data standpoint as well as regulatory development. These compounds have been phased out of production in the Western Hemisphere, and as such, we can see a commensurate decrease in concentrations in biosolids over time. The currently observed concentrations may be explained because they haven't gone to zero. They can be explained by legacy introduction via landfill leachate, possible introduction of film-forming foams in the water system. But it's also most important to point out that consumer products are still imported, which still contain PFOA and PFOS. And given the long half-life in humans, like I mentioned, we will continue to release these to the sewer. So as I mentioned previously, Michigan has completed a fairly comprehensive study of wastewater treatment facilities. The next few slides present summary data provided by Eagle in Michigan. This figure compares the measured PFAS and biosolids through the Eagle study, as well as comparing that to previous published studies in the US and other countries. You can see that the concentrations observed in the Eagle study are in line with the studies that have been previously published in peer-reviewed literature for US, Australia, and Switzerland, supporting the prevalent use in modern developed society. The concentrations are generally between the tens and hundreds of micrograms per kilogram or parts per trillion. The lower averages of this more recent Michigan study may also support what I just talked about with the impacts of the PFOA and PFOS phase out, as shown on the previous slide. And of note, they also included Kenya through a 2015 study, which shows a much lower concentration, supporting a less industrialized and consumer product society, showing lower concentrations of PFOS in its biosolids. This figure shows a summary of all the investigated wastewater treatment plants' PFOS concentrations measured during the study. So these are just individual plants organized from lowest concentration to highest concentration of PFOS in the biosolids or sludge. And the concentrations are on a logarithmic scale in parts per billion or micrograms per kilogram. You can see that the average and median PFOS concentrations were identified at 195 and 13 micrograms per kilogram, respectively. This set of data includes wastewater treatment effluents with known industrial effluent contributions to the treatment plant, and they've identified these as those purple bars to the right side. And you can see that the industrial impacted sites contribute the highest PFOS concentrations. Without these plant contributions to the data set, the maximum PFOS concentration is less than 100 parts per billion or parts per trillion rather, and the average is 16 micrograms per kilogram, or parts per trillion. That is a typo on there. It should be parts per trillion. And as of note, I included the mains biosolid screening value that I mentioned previously, and you can see that all but 4 biosolid samples actually exceed this value. And lastly, here's a summary of the data from a paired set of wastewater plant effluent concentrations, the resulting biosolids concentrations, and then the soil, groundwater, and surface water concentrations that were associated with these plants and these areas where the biosolids were applied from these plants. And this is all again for PFOS. I've also included the screening values that we presented earlier for biosolids and soils, and I also included what Michigan has for proposed drinking water MCL of 16 nanograms per liter, an existing ambient water quality standard, which is actually a promulgated rule of 12 nanograms per liter. So you can compare the different concentrations that were observed between the non-industry impacted and the industry impacted effluents and biosolids concentrations, and the resulting soil, groundwater, and surface water concentrations that were associated with those facilities. These values provide a decent snapshot comparison of the various media to in-state or other state screening values, guidance values, and regulations. And you can see that depending on what values you're comparing to, there could be some concerns. Of course, a lot of those soil values are not in state for Michigan, but just as a snapshot comparison, it's a wide range between 0.22 and 25 micrograms per kilogram, but clearly there's a number of those facilities that could be above those ranges when it comes to the actual applied soil concentration. So I'd like to talk a little bit about how PFAS and biosolids can be treated. I'm just going to touch on this very briefly. I think we're going to get into more detail about that with the next presenter. Here's a summary of some recent research from Dr. Linda Lee's group at Purdue regarding PFAS and biosolids through various treatment processes. The stacked bar colors represent the different PFAS compound categories. So if you start on the right, you can see that the lower temperature hydrolysis has really no impact on PFAS concentrations. And this is not, I guess, unexpected. Measurable PFAS compounds that in our measurable list of the 30 compounds or so, what we consider those terminal end products, those are often considered not volatile, and most have boiling points greater than 200 degrees C. And if we move to the left, the next category is blending with bulking agent, such as wood chips and dust. This effectively reduces the mass concentration, primarily through dilution, and we see that happening quite effectively with this data set. The last set to the left is rotary drying demonstrated at 480 to 650 degrees C. So the rotary drying demonstrated a 53% increase in measurable PFAS. There's 2 phenomena that are actually occurring here. Of course, in a drying situation, we have a loss of water mass, but at the same time, these temperatures are above the typical PFAS boiling point. So the second phenomena is that PFAS volatilization is occurring. At shorter heating times and higher moisture concentration, most of the energy will obviously go into driving off the water. However, there is some fraction of volatilization occurring. So the observed increase is primarily a function of increasing the overall mass concentration through the loss of the water mass in the biosolids, but giving the starting moisture content, if the increase in PFAS concentrations were looked at, they'd be much greater if volatilization of the PFAS didn't occur. So that's why we only see 53% increase instead of a much greater percent increase, because we're balancing the mass increase with the losses due to volatilization. So windowing in on that time temperature in a bit more detail, here's some data from some various studies of desorbing PFAS from dried solids. You can see the relationship between time and temperature. At elevated heating times, the PFAS are volatilized more rapidly, resulting in greater percent removal at shorter processing times. It should be noted that it's strongly believed that destruction of PFAS compounds don't occur at temperatures below 1,000 degrees C. So even at these elevated temperatures tested, the removal of PFAS is most likely a function of volatilization. And this is a significant area, as I mentioned earlier, with EPA, with the PIT program, where they're really taking a hard look at this from a air emissions standpoint of what actually does get destroyed. Are there secondary byproduct compounds that are formed at these higher temperatures? So that's a significant part of the study of the PIT right now. I should also mention that we've recently completed some testing of biosolids in an elevated temperature pyrolysis system. And unfortunately, I didn't have the data in time due to the COVID to be able to present these, but we just completed the testing a couple weeks ago, and we focused on the solid, liquid, and air fractions for PFAS to quantify the distribution and mass balance across the complete system, including the air component. So related to pyrolysis, since I didn't have our own data to show, I actually did want to show some representative data of biosolids. So Bioforce Tech has a system operating in Northern California, and they collected a sample of biosolids both before and after treatment. And these data are consistent to what we've observed elsewhere, and hopefully we'll see out of our data set, which are that the PFOA and PFOS are all reduced, as well as the other PFAS compounds are reduced to non-detect after pyrolysis at a high temperature, in this case 600 degrees C. And at these temperatures, off-gas treatment would be required, as I mentioned, which is what this field scale system includes. So in closing, I'd like to just wrap up with some summary thoughts for the manager of utilities and biosolids in this increasingly evolving world of PFAS around this arena. So one is obviously follow the studies with actual data. It was just as an aside, living in New York and in the COVID issues, we had regular daily inputs from our governor on COVID, and I thought it was very appropriate in that situation that he was very clear every day to say that he's following the data and in looking at actual facts, and there are a lot of different opinions floating around PFAS as well, and so following studies with actual data is highly recommended. Following the regulation development, each state is on its own course to some degree, and the pace of regulation development, especially around the wastewater and biosolids arena, is on the rise. And so keeping a close eye on regulations development is certainly very important. If you haven't done it already, update your biosolids management plan. Developing a flexible biosolids program that can be modified as these regulations or these public demands require is certainly key. If you haven't done it already, you could consider testing your solids to understand the PFAS levels that are currently existing. In the case of Michigan and other states, they're certainly looking upstream for industries that may use PFAS and in looking at point source reductions to start limiting the load to the plant. in being prepared for questions as they come from the public, because they will come if they haven't come already. And lastly, as you can see in the slide here, there's several good resources and probably some others that I've missed with fact sheets that are available, and some good information of compilation of data and compilation of a lot of other information that's useful. So that's what I have. I appreciate the invite from the Mid-Atlantic Biosolids Association to contribute to this webinar, and I thank you for your time, and I think we have a few minutes possibly for questions.
We had 2 questions. We're running a little bit behind. The first one, do you have any insight on possible listing of PFOA, PFAS on the CERCLA Superfund list? EPA said they're trying to get them listed this year.
Yeah. Well, I should say yes. I'm certainly aware of that, but unfortunately, I don't have any insight of that moving any further forward. Related to TSCA, I just saw that a bill was passed at the end of last month in June that is only focused on longer chain carboxylic acids and perfluorinated sulfonates to be for manufacturing in use in industry for the EPA to be notified, but it stopped short of listing them as a hazardous waste or anything like that. So that process is still pending.
Okay. And other question is, what's the fate of the PFAS across the wastewater treatment plant? Of what comes in through the influent, what portion leaves in effluent, and what portion leaves via the biosolids?
Well, I guess in general terms, the fate is I showed on that one slide, is that all your PFAS plus some will likely be coming through the treatment plant. There is partitioning of the longer chains that are more prevalent into the biosolids as opposed to the shorter chains or carboxylic acids. But quite frankly, because most of the biosolids are a large percentage of water, at least initially until dried, the mass balance calculations through Water Research Foundation and other researchers, are currently being developed for a more definitive number. But I would generally say that given the high liquid content of your biosolids, you could generally say that it's reasonably proportioned in fairly common distribution between the effluent concentrations and the biosolids concentrations.
All right. Well, unfortunately, that's all the time we have for questions for Dr. Grieco. Please continue to send questions, and if we can get to them at the end, we will. Dr. Grieco, thank you very much. If you could stop sharing your screen, we'll turn it over to Sudhakar.
I'm trying. Hold on a second. Stop share. There we go.
All right. So our next speaker is Sudhakar Viswanathan. He will be presenting Is Complete Destruction of PFAS and Sludge Possible? Experimentation and Challenges of Combining Thermal Dryer and Thermal Oxidation to Treat PFAS-Laden Sludge. Sudhakar is responsible for developing biosolids and bioenergy projects for Veolia, a world leader dedicated to water, waste, and energy management. He has a master's degree in environmental engineering from Syracuse University and has varied experience in roles that include research, development and industrialization, product management, and more recently, business development. Sudhakar has 20 years of industry experience, formerly with Suez and currently with Veolia, two of the largest environmental companies in the world. Sudhakar has authored over 25 papers and has presented at regional, national, and international conferences. Sudhakar, over to you.
Thank you, Lauren. Thanks to Maba for this opportunity. I'm going to try and share my screen. Let me know if you can see it.
Yep, I can see it.
All right. Thanks everyone for joining us this afternoon for the session. As you can see, my presentation obviously has a pretty lengthy title, but the one question we are trying to answer through the work we are doing here is complete destruction of PFAS and sludge possible? That's the question we are trying to answer. And my presentation is going to follow along this overview that I have here. In fact, Scott covered a lot of what I have in my first deck of slides, which is what is PFAS and how what you should expect in your sludge and such. Then I'm going to focus on the technology and follow it up with the research work we're doing, and then close with my summary slides. All right, so I think this part of the presentation is going to sound almost redundant because Scott covered most of it. PFAS, obviously, you know, there's plenty of compounds that fall in this category. I believe there's over 4,700 of those compounds being recognized, and there are new compounds that's invented or prepared in laboratories, like Genex, for example, is a new one which is being used as a substitute for the traditional Teflon material and such. They all tend to still fall in the same category. Some are in the borderline, but in general, there's plenty of this material that's floating around. As Scott mentioned, it's in basically everything from what we use on a daily basis, including food and such. So it's pretty extensively available in the developed part of the world. The unique thing about this material is it's very persistent. That's why it's used in things like non-stick cookware, because, you know, they're resistant to high heat, and they tend to they tend to last forever, and that also makes it very difficult for treatment or destruction. This material is also toxic, so it is considered as an endocrine disruptor, and it is carcinogenic to some extent. There were some studies done in the late 80s and early 1990s where they found this material to cause cancer, and that's something of a concern for everyone, because this material also bioaccumulates, which, as Scott mentioned, which means it's once it gets into your body, it doesn't leave very easily. The half-life of this material is anywhere between 8 and 12 years, depending on which of this 4,700 compound is in your system, and it's basically in all of our blood. So, which brings us to the next question, which is PFAS in our sludge? This question is almost redundant, because if it's in our blood, I think we should expect it to be in our wastewater as well, and, you know, in our sludge as well. So here's a list of all the military sites that we know of that has some level of PFAS contamination. And again, this comes from the firefighting foam, which is extensively used in fire drills and things of the nature. It's in drinking water. As you can see, there are some states that show dominance of PFAS in drinking water, and some of the states don't. That does not mean that your drinking water does not have PFAS. It probably means that your particular drinking water facility has either not tested, and if they have tested, they haven't tested for all of the compounds, and if they have tested for all of the compounds, they haven't just informed you yet, or that data is not publicly available yet. And then there are some other known sites. For example, landfills are another source of PFAS, so that's probably what falls into the other category. But in general, we should assume that there is PFAS in your sludge. If you test it, you will find it. So how do you destroy PFAS? So again, you know, when we started researching into ways of figuring out how to get rid of PFAS from sludge, we did what we naturally do, which is go look for literature and see if someone else has done any studies in the past that could give us a direction. And we found a few studies specific to solid phase, solid matrices having PFAS, and we found that most of those studies led to a thermal degradation as the way to treat PFAS. And there were some additional studies that indicated that if you were to pre-treat the sludge with some chemicals, there's potential for reduction in your emission when the material is combusted. So with this information in hand, we looked at potentially figuring out how to go about testing or demonstrating the efficacy of any thermal treatment. So we started with a very broad picture here. So this is a graphic from GWI, and it basically shows all the sludge management options that's out there. And as you can see, there's a section that's specifically dedicated for thermal reduction. So we focus predominantly on that, but we also looked at some options where you could potentially dry the material prior to thermally oxidizing or thermally reducing. So we picked a few of these technologies and did further study on it. We obviously chose an indirect thermal drying system because that is in line with the technology that we have available, and so we had some data that we could support in that initial study. Incineration was another one, and specifically fluidized bed incineration. Again, this is a technology that we are very familiar with and we have in our portfolio that we could leverage. We also looked at supercritical water oxidation. Again, when I say there's a local university here, I'm pretty sure most of you know, it's called Duke. They are doing some work on supercritical water oxidation. So we did visit and had conversation with them to see how their work, particularly with respect to PFAS, was and how it would impact possible treatment. And we also looked at some literature on gasification and pyrolysis. Again, similar to what Scott mentioned, there are some companies that have done this work. We did not do any specific work on this, but we did look at them just to compare those technologies to see what makes sense in our focused research that we are currently undertaking. So we narrowed it down to these 4 categories that you can see here: incineration, supercritical water oxidation, pyrolysis, gasification. We kind of put them in the same bucket, but as there is some distinct difference between those 2 technologies. But in general, for the purpose of what we were trying to do, we thought it would be best if you combine them together. The last one is a furnace. Basically, it's a biomass furnace, and that would follow a thermal drying process, which is where the thermal dryer comes into picture. When you compare these on a side-by-side basis, when you look at the temperatures at which these technologies, each of these technologies are optimally used at, you can see there's a wide range. And as you can see, some have a very narrow bandwidth or narrow range of use, whereas some are a lot more flexible. When you look at the sludge retention time, or the time the sludge spends inside the reactor, in each of the cases, again, you can see some are really short, some are really long, and some have flexibility to be either or. And then we looked at the amount of time the off-gas, or sorry, the flue gas spent within the reactor, to further go, maybe at some additional thermal degradation. And again, some are small, some are large. Some come in the form of syngas that could be further used in the process itself. And also we looked at the concentration of sludge that you would be feeding into the reactor. And the reason why I bring this up is there was a question at the end of the previous presentation where somebody asked what would be the impact of the incoming PFAS in the liquid stream that would potentially impact the solid. And I think Scott mentioned that a lot of this liquid that's in sludge, in the case of the incinerator, it's probably, the other 75% of the material is water, and 85 in the case of supercritical water. That portion of the liquid could potentially have a lot of the precursors, which through these processes could actually become terminal. In fact, could elevate the overall PFAS that you need to manage through this treatment. So we tend to lean on the more drier material, as in the pyrolysis or in the furnaces, where you have very little water. So the water matrix, whatever the PFAS that's coming in the water, is treated on the water side or the liquid side of the treatment, allowing for us to focus more on the PFAS that's in the sludge. So these are the pre-treatment that's required for each of those technologies. And again, for both pyrolysis and in the case of a furnace, you need a dried material, so you require a dryer in addition to dewatering. And of course, the end products, in some cases you get ash, in some other case you get char, biochar, whatever the case might be, water in the case of supercritical water. And again, some of these technologies, again, are proven or older or mature technology, whereas some are new. So with this data in mind, we decided that we are going to focus on technologies that we could work best with. But before I go to that, I also want to mention that a lot of the study that's done on PFAS thus far by different providers of these technologies, or manufacturers, or people who research in this field, they tend to focus on the primary end product, which is either ash, water, or char in this case. But there's not a lot of information that's out there in terms of what happens to the emission. There is some study that was performed earlier this year in Manchester for a SSI, for a sludge incinerator. I believe it's a fluidized bed, but we haven't seen any data from it. We're trying to perform a mass balance around the entire process, not just in the ash component, but also in the emission component. With that being said, we focused on the furnace and the dryer as the primary vehicle for our study. We wanted to use that as the technology that we would which we would further in the study. And just a quick spotlight on how this technology is set up. Basically, you would bring in sludge anywhere between 15% and 30%. This is dewatered cake, and you would run it through a dryer. In our case, we're using a Biocon, which is a medium temperature belt dryer, and that would produce a biosolids that's a Class A product actually, which would be 90+% dry. In our case, it's close to 95% is what's coming out, which is used as a biofuel in a furnace, which we call the ERS. It's primarily used for energy recovery, hence the name ERS. And the flue gas from the furnace would then be captured, and using a heat exchanger, either an air-to-air or air-to-thermal oil heat exchanger, we would capture that energy and put it back into the dryer to drive the drying process. If all things go well, you should have enough energy, especially if it's an undigested solids. You would have enough calorific value to drive this whole process and become fully thermally self-sufficient. How does it look in the real world? So as you can see on the left side, the dryer looks like any other belt dryer I would imagine. And the furnace is a relatively small component. It's a step-grade biomass furnace, very commonly used in Europe, especially in the Scandinavian part of the world, for using wood chips as a source of fuel. And the heat exchanger could be either like the one you're seeing here, or it could be an economizer, or tube and tube, or tube and shell, whatever the case might be. So how does it look in a full scale? So this is not a new technology by any means. We have a plant that's been in operation for close to 12 years now, or maybe 13 years now, where the same exact technology has been applied. And but in this particular facility, we are not using it as part of PFAS treatment, but it's more for the energy recovery aspect of it. There's the dryer, which operates between 180 and 350 degree Fahrenheit, and then you have the ERS, which is capable of going up to 2100 Fahrenheit. And the heat from the exhaust is captured through a heat exchanger prior to the air being recirculated back into the dryer. At this particular facility, we have a dry treatment for the initial for particulates, where we add some GAC, granular activated carbon, for mercury removal. And there's also an option for wet treatment for further treatment. But when this plant was built, there was no SSI regulation. The MACT was not enforced. So it's treating to probably a tier 2 or tier 3 level of treatment right now, triple L maybe. But we can design it to meet the Quad L regulations as well for the new SSI. What we don't know, or what we have not measured thus far, is there any PFAS that comes off the emission? And I think that's where the research focuses on. So jumping quickly on the research, this was done on a laboratory scale. We partnered with University of Dayton. The reason we partnered with them is when we did all of our literature review, we found a lot of work that UDRI had performed in the past for both EPA and DuPont and others, with similar study where they looked at the fate of PFAS in different materials. We figured if they should be able to do the same thing for us with sludge. It's a self-funded study, so we didn't look for any grants or any support from any other organization. Again, that was the intention was to commercialize this technology, so we didn't want to get any funding from elsewhere. We did the study in 2 different phases. The first one was basically the transport, the science of PFAS undergoing thermal decomposition. In the second study, obviously, we looked at the fate of PFAS, what happens in all 3 phases, which is solids, the liquid, and the gas phase of the combustion. And the deliverables was really to figure out a fluoride mass balance across the entire process. As I mentioned, we had to look at what happens to PFAS once sludge is thermally oxidized. What happens to the PFAS if any remains in the ash. At the same time, we had to look at what happens in the emission. And we also had some additional work done to make sure that none of the PFAS is actually accumulating within the system itself. And again, we wanted to have a data-driven solution for the real world, so we didn't want to just build the system. The worst thing we could do is remove PFAS from sludge and put it in the emission, and that's not something we wanted to do. And also, we had to figure out if there's any additional air pollution control technology that we need to add for additional chemicals or components that we have to deal with, and we anticipate it to be something like hydrofluoric acid or hydrogen fluoride coming in because of combustion of PFAS material. So the lab setup is something along this line, and it's a reactor with a quartz center. Just to simplify this, there's a schematic that you can see here. The furnace is basically a quartz reactor where we could elevate the temperature and control it at various required temperature profiles. We would introduce a sample through a pyroprobe in a sample board, and then we should be able to provide any excess air or any other chemical that any other gases that we may need to add for subsequent cleaning or capturing some of this emission and such. And then we will combust the material. We'll capture the emission through these impingers in the back here, and we would then do some steam cleaning and things to ensure that there's no PFAS that accumulates within this reactor. And we do this for every study, every test, to make sure that we capture all 3 phases of this material within the system. In terms of the challenges, the very first challenge we had when we wanted to do the study was to get sludge which had a high concentration of PFAS. You know, as common as it is to have PFAS in sludge, high concentration is not generally easy to locate. And even when we found a few plants that qualified to have this high amount of PFAS, it was really difficult for us to get them to sign a non-disclosure agreement because they didn't want us to even accidentally disclose the location on the data from this test. So one thing we did was we redacted all location information from samples as we received the samples. As you can see, the bucket itself in which we shipped empty buckets with scoops and such, and we got it back. We made sure that the bucket itself does not have any location information, so it would come in a different packaging, and then we would destroy the packaging and we would put all the buckets in one room, so we ourselves didn't know where this material came from. And definitely after we dried it up in our laboratory to bring it up to the 90-95% dryness for study at the UDRI lab, before we shipped it out, obviously, you know, we shipped it out as with no labeling to say where the sample was, because we ourselves at that point did not know where the sample came from. So finding and getting people to share the sludge was one of our biggest challenges. The second part was basically working with the stoichiometry as opposed to the limitation of the test kit itself. We had 3 impingers at the very beginning, and then we had to increase the volume to 4, and then we had to consider slipstream for the emission capture, because the air that's required for the stoichiometry to completely combust this material was far greater than the resident times that we needed in each of the impingers. So that was another challenge that we had to overcome. The third one was the size of the sample we combusted. Those reactors, even the laboratory setup was capable of taking anywhere between 2 and 5 grams of this material for combustion. So it's a pretty small volume. The amount of ash that would generate from a combustion would be about 10% of whatever the volume we put in. That was too small of a volume for the laboratory to measure any PFAS from this ash. So we had to repeat the test numerous times to collect more ash. And as I mentioned, each time we did this test, we had to do a complete clean out. So it took a lot of time and effort, and obviously, you know, those things end up translating into money. And finally, of course, you know, in order to have the full flow rate balance, unlike any other study that's done on a full-scale basis, here we had the luxury of actually washing down the entire reactor with steam to basically scrub anything that could have potentially gone and gotten stuck around the reactors and in the tubings or whatever the case might be, so that we were making sure that this compound just doesn't come off sludge during combustion and then sticks to the insides of the reactors, and then we may not see anything in the emission, but it still exists inside the reactor itself. So we had to make sure that that was something that we were able to do successfully also. In terms of the timeline, we were really hoping that we would have gotten done with the study by second quarter of 2020, and as you all know, that didn't happen because of you know, the pandemic. But we just recently, actually about 2 weeks ago, we started the study back on. So we are some of the results is trickling back in. It takes about 3 weeks after every run to have usable data. And I think with that, we should have the report done by the end of the year. Hopefully, we should have it published in some journal by the first quarter of 2021. Some early results. So we did about 5 thermal, transfer efficiency studies, basically to even see at what temperature, at various temperatures, we wanted to see how PFAS goes from the solid phase to the liquid and gas. And then, you know, obviously, you know, we had to do some emission efficiency as well there. Stage 2 is on, quite a few studies done at the temperature, at lower temperatures, but we are going to be studying the higher temperature for further analysis. So, and I'm going to skip this slide here and quickly go back to the summary. So the question is complete destruction of PFAS and sludge possible? I think that's the question we try to answer, and the answer is yes. Under the right conditions, you could effectively destroy PFAS of the compounds that we can measure, which is about 24 compounds, and the total oxidizable precursor assay would still yield a good 90 to 99% destruction. The other studies that we are still waiting on is the initial emission data shows that it's promising that in our case to not have any residual PFAS in it, which is good because, as I mentioned earlier, the last thing we want to do is take it out of the sludge and put it in the air. We have to consider hydrofluoric acid management inside our air pollution control train. And there's a cautionary note here. I just said that if you have an incomplete combustion, we have to study further to ensure that your PFAS is not in your emission. With that, I should be able to take some questions.
All right, thanks, Sudhakar. So we have one question, and it is, where is the Biocon ERS installation? Have they done testing to show PFAS removal?
So, so the question was, where is the Biocon ERS, and if they have done any testing to show PFAS destruction. The facility is in Buffalo, Minnesota. It's about an hour northwest of the Minneapolis airport. It's a suburb of Minneapolis, actually. They have been using this for about 12 years now. But unfortunately, I won't be able to share any PFAS information about that specific plant because they are, we have done some independent work with their data, but they haven't done any that's publicly available right now. But there is some information on the sludge and the ash part of it, but on the emission side, I don't believe they have any information yet.
All right, awesome, thank you. So that's all the time we have for questions for Sudhakar. Please continue to use the Q&A feature to continue asking questions, and we'll get to them time permitting at the end of the session. Sudhakar, thank you again, that was fantastic. So on to our next speaker, Dr. Steven Zemba. Dr. Zemba will be presenting a technology overview on methods of assessing health and environmental risks of organic micropollutants and biosolids. Dr. Zemba currently works for Sanborn Head & Associates, where he works on projects involving fate and transport modeling, exposure assessment, and risk assessment. He's a frequent presenter at conferences and has published numerous articles on topics related to environmental modeling and risk assessment. He attended Carnegie Mellon University and then earned a master's and PhD in mechanical engineering from MIT. Dr. Zemba was recommended to speak at this webinar series by Ned Beecher of the Northeast Biosolids and Residuals Association for the assistance he's given thus far in framing the risk of biosolids-borne PFAS. Dr. Zemba, over to you.
Thank you, Lauren, and thanks everybody for sticking around. This is supposed to be the technology spotlight portion of the presentation, and I was told to try and sell Sanborn Head. I'm certainly sold on it. I joined Sanborn Head about 5 years ago. I love the company, and I encourage you to go to our website and check it out. We have 4 business areas that all work together, but I think the message there is the accurate one. We're a relatively small company, about 130 people, and you know we're big enough that we have some really strong technical specialties, but we're also small enough to work very closely with people who've been around for a while. Mostly, you know, our concentration is in New England, but we now have a Philadelphia office. One of my colleagues, Colleen Costello, is on the webinar today too, and I encourage you to contact her at the end, you know, if you have any consulting needs. And in terms of the areas of PFAS technical depth, I'm going to focus on PFAS here. We've been looking at a lot of sites in the Northeast and other parts of the country, sampling for PFAS, trying to figure data out. I think, you know, the resounding theme of all 3 of these presentations is going to be, it's hard to figure out PFAS. The fate and transport of it is very complex. It's multiple chemicals, multiple things going on at the same time. Some of the other ways we help clients, though, are through public outreach and communication, just trying to calm people down in some cases. A little bit of, I'm going to call it advocacy, in the sense that, I don't think all voices are being heard about PFAS and the impacts of them right now. Certainly, it makes sense to respond to various proposals that are out there from regulatory agencies, and we've helped Advitra in particular to do that in the Northeast. And some of the other specialists we have are just looking at data and understanding data. And I thought I'd try to build on what Scott was presenting before and talk a little bit about PFAS in the environment. Something I want to call everybody's attention to, though, are surface water standards or ambient water quality criteria. For those states that have looked at surface water standards for the protection of human health through fish ingestion, and looked in particular at the chemical PFOS, uniformly every state that's looked at that has come up with surface water screening levels that are lower than drinking water standards. And the drinking water standards have kind of limited applicability. You have to have a drinking water source for them to count. I mean, they can be turned into groundwater standards, which makes them important in other reasons. But the surface water standards are going to have general applicability. And it's not only going to affect biosolids, of course, it's going to affect discharge from wastewater treatment plants. That's a big deal that's coming down the road, I think, and everybody should be aware of it. I'm going to talk about two sites specifically on biosolids, and one of them is in Vermont. And these are sites where biosolids have been monitored, meaning they have groundwater wells to look at the impacts of biosolids on, say, groundwater sources. And the importance here is that, we all want to think that it's okay to apply biosolids. We've been doing that for many years in many places. I'd like to continue doing that. But the question, as kind of Scott alluded to, is, are those biosolids leaching out PFAS? And this is a site in Vermont where there have been repeated applications of biosolids over years with 3 fields. And the thing to look at is on the kind of left side there, the part per trillion numbers are the groundwater monitoring data. Vermont has a standard of 20 parts per trillion. And at these particular sites, and these are very site-specific results, you can see that the 20 part per trillion number kind of gets blown out of the water. This would be a significant issue if there were drinking water wells nearby. Thankfully, there aren't. But there do seem to be impacts coming from biosolids applications at these sites, or at least sludge application. I want to get to another famous site in Maine, infamous site at this point. Some of you probably have looked at this in various ways, but this is the Stone Ridge Farm, and it was a site where the farmer found PFAS in his milk supply coming from his dairy cows. There's been a lot of monitoring of a lot of different media at that site. There is a drinking water source nearby. It hasn't been affected at the 70 part per trillion level that we care about in Maine yet. But certainly groundwater has been affected. But one of the complications to this site is that they also accepted, we think, paper sludge for a while. So some of these sites are complex. They involve maybe over-application of biosolids in some cases. But this did take Maine down the road of establishing those screening concentrations that Scott alluded to for PFOS of 5.2 parts per trillion, or for PFOA of 2.5 parts per billion, per billion on that scale. There's also one for the 4-carbon sulfonic acid. That one really isn't affected by much, but since there was tox data, they derived that 1900 part per billion number, just not very consequential. You can go online and download this data, which is what I did for the Maine sludge data. Maine has gone out and required sampling of the sludge and also making those data available online and get reported to them. And here I'm comparing the two bin graphs to the screening concentrations, PFOA at 2.5 parts per billion on the left, and PFOS at 5.2 parts per billion on the right. And you can see, especially for the PFOA, many of the sludge samples don't make it. And that's consistent with the data that Scott was showing in the 10 to 100 part per billion range for PFAS in sludges. You're not going to be able to meet those very stringent standards, which kind of puts you in a quandary. Is it really safe to land apply biosolids? That question is going to come up a lot. Something we should think about, and I'm changing topics quite a bit here, but PFAS have been around for quite a while, as we heard from Scott, and there has probably been long-term atmospheric deposition from all the stuff we put up into the air that came back down to the ground. We did a study in Vermont with the University of Vermont looking at kind of pristine soils, and this is Vermont, so we're pretty remote. we were finding part per billion levels, low part per billion levels in a lot of those pristine soils. The median concentrations of PFOA, that's a little typo though, PFOA and PFOS, that should say, the background level is about 1 part per billion if you sum those two up. And the 1 part per billion is about an order of magnitude to 2 orders of magnitude lower than what you see in sludge. And the lesson from that is that sludge accumulates PFAS. And we kind of know that because it's accumulating in the wastewater treatment plant. So the main standards are screening level concentrations and other standards for soils, which you could apply to biosolids if you think about it from a leaching perspective. Those are coming from very simple models that we have for predicting the fate of organic chemicals in soil. And I've got that thing written out there in terms of the equation. They depend on partitioning coefficients, things like the organic carbon partitioning coefficient, which is a tendency of a chemical to stick to solids, or Henry's law constant, which is its tendency to go into air. If you apply those equations to PFAS, and it's a difficult thing to do because properties of PFAS are difficult to even measure or characterize because these are surfactants and they behave very strangely in soil. But it turns out that when you apply these models with some values, you can get that out there in the literature for properties, quote unquote. What you see is that you don't need very much in soil to drive significant levels in groundwater. And that's kind of how the state of Maine gets to those relatively low numbers being the acceptable levels for PFAS in sludge. I just want to finish this with all models are wrong and some are useful. The model in this case is not a very good one for PFAS. And unfortunately, we don't have a better model at this point, but that's kind of an area that we need to look at and research. I think in summary, what we're going to see down the road is that there's going to be more monitoring of sites. I think that biosolids applications should continue. I think in most sites it's probably acceptable and you're not going to see excessive groundwater impacts. Want to watch the surface water concentrations and those standards coming out. If you have questions, feel free to call me or contact me or contact my colleague Pauline, who's in the Philadelphia office. And I'd encourage everybody, and this is something Scott worked on with me and many others, it certainly wasn't us alone, but the ITRC has wonderful resources out there for just educational materials on PFAS, and I encourage you to go to that website and check out that information. I think that's about all I have, and I think I got us back on time. So happy to take some questions.
Yep, we are back on time. All right, I don't have any questions, but like Dr. Zemba said, if you do have any, feel free to reach out to him. All right, and I think that's about it. That's what we have for today's webinar. Thanks everybody for your questions. Thanks to Dr. Scott Grieco, Sudhakar Viswanathan, and Dr. Stephen Zemba for presenting. As a reminder, the link to the recorded webinars, as well as credit certificates and transcripts, will be emailed to all the attendees at the end of the MABA webinar series by mid-August. Please be sure to take note of the next webinar in the series, which is next Tuesday, and that's on oxidative processes for biosolids management. We hope everyone can make it. Thanks again to the speakers and all the attendees. Have a great afternoon.